As we know, the current coronavirus disease pandemic has become a worldwide issue for over a year. Since the World Health Organization first received news of a viral pneumonia in China on the 31st of December 2019, the virus has then developed into a pandemic. And now, with over 100 million cases and 2 million deaths worldwide, we are increasingly in the need of a vaccine or drug. In order to develop a vaccine or drug, a key part of the process is to decode the three-dimensional structure of the severe acute respiratory syndrome coronavirus 2 or SARS-CoV-2, the virus that results in the coronavirus disease. This would enable researchers to understand the structure of the SARS-CoV-2's protein, which allows finding a location for drugs to latch on. But how would we do that? By combining physics with biology. With atomic/molecular structure determination methods such as X-ray crystallography and cryogenic electron microscopy, we are able to analyze the structure of the SARS-CoV-2. The most widely utilized technique among researchers is the X-ray crystallography. It involves crystallizing the sample and exposing X-ray beams to the crystals of the proteins in the molecules, where the beams would be diffracted by atoms present in the protein crystal. Depending on factors such as the organization of atoms and the number of electrons in the atoms, the X-ray beam will be diffracted into multiple specific directions. Now, what researchers analyze are the angles and intensities of said diffracted beams. As a result, they would be able to obtain a diffraction pattern and produce an electron density map, enabling mapping the protein's 3D structure. However, as not every protein could be diffracted using X-ray crystallography, researchers divert to cryogenic electron microscopy or Cryo-EM. This method involves cooling samples to cryogenic temperatures, which is from -150 degrees Celsius to absolute zero. Next, researchers store the sample in vitreous water conditions. From the frozen samples, researchers could extract multiple two-dimensional images, which could be processed using a reconstruction software to generate a three-dimensional model. The advantages of X-ray crystallography is that it produces a high-resolution image, has a wide molecular weight range, and is well developed. Unfortunately, it requires certain conditions for crystallization and could only work with limited types of samples, such as how it is not applicable for larger molecules due to its molecular weight and poor solubility. On the other hand, the advantages of Cryo-EM is that it is simple to prepare the sample, it requires only a small sample size, and the structure could be in its native state. However, it produces low-resolution images, it is useful only for high molecular weights, and the equipment for electron microscopy is costly. Nonetheless, both methods complement each other and have played a pivotal role in the research of the structure of SARS-CoV-2. Various research institutions have been utilizing these methods in the journey to analyze the SARS-CoV-2, from the Advanced Light Source at Lawrence Berkeley National Laboratory to the UK's Diamond Light Source. So, with the helping hands of physics, specifically through electromagnetic radiations in the form of X-rays, as well as quantum physics, research of the SARS-CoV-2 has been developing well. And, as a wise man once said, the next time someone tells you that biology is your only weapon against a pandemic, you tell them that they are dead wrong.